In the last video, we looked at something called the generalized mean value theorem, and then we applied this generalized mean value theorem to prove the 0 over 0 case of L'Hopital's rule. Now we want to revisit this theorem and use it to prove the infinity over infinity case of L'Hopital's rule. So let's go ahead and recall this generalized mean value theorem. It says that if we've got two functions f and g, and they are continuous on a closed interval a, b, and differentiable on the open interval a, b, then there exists a c on that open interval such that g prime of c times f of b minus f of a equals f prime of c times g of b minus g of a. But maybe the better way of looking at this arrives when we have the case that g prime of c is not equal to 0. And in that case, we can write f prime of c over g prime of c equals f of b minus f of a over g of b minus g of a. Okay, and then also I'm just going to recall the precise definition of a limit because we're going to need that in this setup as well. So we say that the limit as x goes to a of f of x equals L if for all epsilon bigger than 0, there exists a delta bigger than 0 such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. And I want to point out that these absolute value inequalities are equivalent to the following compound inequalities. So here we have x is between a minus delta and a plus delta. And here we have f of x is between L minus epsilon and L plus epsilon. So we'll float between these absolute value inequalities and the compound inequalities as needed. Okay, so let's look at the statement of our infinity over infinity L'Hopital's rule. We want to assume that f and g are differentiable on the open interval a, b, and g prime of x is not equal to 0 for all x on that open interval. Then next, if we have that the limit as x goes to infinity of f of x is plus or minus infinity, and the limit as x goes to a of g of x is also plus minus infinity, then if the limit as x goes to a of f prime over g prime equals L, then the limit of just the quotient of the two functions equals L. Okay, so let's maybe get to this proof. So we want to assume all of this stuff up here in the hypothesis and this part of the if statement here and show that this, along with this assumption, implies that the limit of f over g equals L. So in other words, let's go ahead and assume that the limit as x goes to a of f prime of x over g prime of x equals L. That's our given. And then also, we want to say that we have been given some arbitrary epsilon bigger than 0. And this epsilon is what we're going to use to show that this limit is L using the precise definition of the limit. But before we get to that, we want to build some useful tools out of the fact that the limit of the quotient of the derivatives equals L. So we can find some delta 1 bigger than 0 such that if the absolute value of x minus a is less than delta 1, then f prime of x over g prime of x minus L in absolute values is less than epsilon over 2. So you might say, well, why an epsilon over 2? Well, we'll see why we need epsilon over 2 in the calculation a bit later. But remember, we can make this as small as we want. How small do we want to make it? We want to make it epsilon over 2, where this epsilon was given to us before. Now, the next thing that I want to notice is that this condition implies a little bit more strict of a condition, and that condition is the following. So notice if x is between a and a plus delta 1, then we still have this inequality right here. So in other words, the absolute value of f prime of x over g prime of x minus L is still less than epsilon over 2. Because this absolute value inequality implies like kind of a larger compound inequality, and we're just taking the right half of this compound inequality. And that's because we're only dealing with points to the right of A, so we want to restrict ourselves to that. Okay, so the next thing that I want to do is introduce some notation. So let's go ahead and set t equal to a plus delta 1. But now notice this notation, along with this inequality right here, tells us we can write x as being on the open interval a to t. Now here's a really important thing. We know that f of x and g of x are not really well defined at a. Notice their limits are plus minus infinity. That means they're not defined at a, which means we cannot apply this generalized mean value theorem where the left-hand endpoint is a, because we need continuity at a. So instead, we will apply this generalized mean value theorem where the left-hand endpoint is x, where this x is just some arbitrary fixed number on that open interval a to t. So let's exactly do that. So we're going to set t equal to a plus delta 1, and then we're going to fix x on the interval a to t, and then apply the generalized mean value theorem to, well, we're going to apply it to the functions f, g, and the interval x comma t, where those are both closed. So now we have f and g are both continuous on that closed interval. So what is that going to give us? So that's going to give us the existence of some c on the corresponding open interval x to t, such that f prime of c over g prime of c is equal to f of t minus f of x over g of t minus g of x. Because our left-hand endpoint is x and our right-hand endpoint is t. Okay, good. So we're running out of room. Maybe I'll take the summary of this up to the top and we'll move on to the next step. Okay, so let's see where we are. We're given some arbitrary epsilon bigger than 0, and we took a delta 1 bigger than 0 such that if x was on this open interval a to a plus delta 1, in other words, a to t, where I set t equal to a plus delta 1, then we have f prime of x over g prime of x minus L is less than epsilon over 2. The next thing that we did is applied the generalized mean value theorem to this setup to find a c on the open interval x to t such that f prime of c over g prime of c is equal to f of x minus f of t over g of x minus g of t. Now the fact that c is on this interval x to t, which is a subset of this interval a to a plus delta 1 or a to t, tells us that this f prime of c over g prime of c minus L is less than epsilon over 2 when we put that into absolute values. But what that tells us is that we can replace this f prime of x over g prime of x with this quotient involving just f of x and g of x. So in other words, we're going to take this equation and insert it into this inequality, and simultaneously I'm going to take this absolute value inequality and turn it into a compound inequality. So that's going to give us L minus epsilon over 2 is less than f of x minus f of t over g of x minus g of t, which is less than L plus epsilon over 2. Good. So now let's see what our goal is. So our goal is to find this limit as x goes to a of f of x over g of x. So we've got this thing, which is an expression involving f of x and g of x. So somehow we want to manipulate this inequality so that we can get like the f of x over g of x by itself. So let's see how we can do that. So this step is a bit tricky. And in fact depends on if g of x is approaching positive or negative infinity. And you really have to do it one case at a time. So we're just going to look at a single case. and that is that the limit as x goes to a of g of x equals plus infinity. But what that tells us, well, is that x is growing without bound as x is approaching a. But that will tell us that we can find a delta 2 which is bigger than 0, such that for all x on the interval a to a plus delta 2, we have g of x is bigger than or equal to g of t. So we know that we can make g of x as big as we want it to be, and that's because it's approaching positive infinity. So how big do we want it to be? Well, we just want it to be bigger than g of t, where t was this fixed value up here that depended on delta 1. Okay, and now that's really important because we're going to take this entire inequality and multiply it by something. And so what are we going to multiply by? We're going to multiply by g of x minus g of t all over g of x. And so let's see. It was important to have this g of x is bigger than g of t so that this fraction was positive and so that we maintained the order of the inequality here. So again, I'll let you guys write the details down for what happens if g of x is approaching minus infinity, but a small tweak will get you to the same point. Okay, so anyway, we're going to multiply this inequality by this object, and let's see what we get. So that's going to give us L minus epsilon over 2 times g of x minus g of t all over g of x. And then let's see what we have here. That's going to be less than, well, in the middle is f of x minus f of t all over g of x. So notice this g of x minus g of t got canceled with the thing that's in the numerator. And then over here, we have L plus epsilon over 2 times the same thing. So g of x minus g of t all over g of x. So now we want to go ahead and simplify this thing and move some stuff around so that all we are left with in the center part is f of x over g of x. So our first step in doing that will be to multiply out this side and this side. In other words, the extreme left and the extreme right of this inequality. So let's see what we get for the extreme left. So I'm going to bring this 1 over g of x kind of out front. And then we will have L times g of x minus L times g of t. And then next we'll have minus epsilon over 2 times g of x. And then plus epsilon over 2 times g of t. So that's what we get there. Okay, and then in the middle, we're going to have f of x minus f of t all over g of x. So nothing's changed there yet. And now we need to multiply this out as well. So let's see, we're going to have 1 over g of x, just like we had over here. And then we'll have L times g of x minus L times g of t. So that's good. And then plus epsilon over 2 times g of x minus epsilon over 2 times g of t. Good. So the next thing that I want to do is I will add to all parts of this inequality f of t over g of x. So I'll do plus f of t over g of x, plus f of t over g of x, and then same thing here, plus f of t over g of x. So that's going to leave me with f of x over g of x in the center of this inequality, which is the object that we're trying to find the limit of. So I'm going to go ahead and off the board add that together and do some simplification, and we'll start back up with that calculation. So in the last board, we ended at a quite complicated compound inequality. So I've simplified it a bit and we arrived here. So we've got L minus epsilon over 2 plus f of t plus epsilon over 2 g of t minus L g of t over g of x. is less than f of x over g of x, which is less than L plus epsilon over 2, plus f of t minus epsilon over 2 g of t minus L g of t all over g of x. Now, the important thing that I want to notice here is that this numerator here is a constant with respect to x. Remember that t was set to be this a, which is a constant, plus delta 1, which was a constant depending on our choice of epsilon. So let's just go ahead and point out that this is some sort of constant. Maybe we'll call this constant capital A. And then likewise, this thing over here is also a constant because it only depends on t, L, and epsilon. So we can call this constant capital B. Great. So the next thing that I want to do is take this compound inequality and rewrite it as an absolute value inequality. And we can do that maybe like in the following way. So it's not going to be like quite as tight as we need it to be, but it'll be good enough for our game. So here we're going to have the absolute value of f of x over g of x minus L. But now we want to wrap these two parts together into a package so that we definitely land bigger than this object right here. So let's see how we can do that. So we'll have this epsilon over 2 term, which comes from this guy and this guy. And then maybe we'll say plus the maximum of the absolute value of A and the absolute value of B over the absolute value of g of x, like that. So definitely this object right here, which I'm going to maybe put in green, is for sure bigger than this object right here and that object right there. So we're good to go on this inequality. So maybe I'll go ahead and call this thing that I'm boxing in purple equal to m, just to make us easily write this as epsilon over 2 plus m over the absolute value of g of x. Okay, so next we're going to use this fact that the limit as x goes to a of g of x is infinity. So the limit x goes to a of g of x equals infinity. But what that tells us is that the limit as x goes to a of m over g of x, where that's just some constant, it may be some large constant, but that's going to be equal to 0. Then we can also put absolute values there. So m over the absolute value of g of x, that's going to be equal to 0 as well. That's going to follow from this limit pretty easily. That's like a standard homework problem from a while ago or something. Okay, but now we can apply the precise definition of the limit to this, again, where our epsilon is epsilon over 2, to find yet a third delta. So let's do that. So we will find a delta 3 bigger than 0 such that if x is on the interval a plus delta 3, then the absolute value of m over g of x is less than epsilon over 2. Great. But what I want to point out here is that if this m over g of x is less than epsilon over 2, then that means our f of x over g of x minus L will be less than epsilon over 2 plus epsilon over 2, which is less than epsilon. But what's required there is that our delta is chosen not just to satisfy this condition, but the two previous conditions. So we can finish this off by saying that if delta is equal to the minimum of delta 1, delta 2, delta 3, and x is on this interval a to a plus delta, then we have this inequality right here. So the absolute value of f of x over g of x minus L will be less than epsilon over 2. So that's what we get from the combination of this thing being smaller than delta 1 and delta 2, and then plus another epsilon over 2, And that's from this bit right here, and that comes from our delta being smaller than delta 3. But that's going to be equal to epsilon. So if we look at this part of the inequality and this part of the inequality, we see that we have satisfied the definition for this following limit. And that's a good place to stop.